In this video, we will design a dynamic programming solution for the knapsack with repetitions problem. Recall that in this problem, we are given an unlimited quantity of each item. This is the formal statement of the problem. We are given n items with weights W1, W2, and so on, Wn. And its values are V1, V2, and so on, Vn. By capital W, we denote the total capacity or the total weight of the knapsack. And our goal is to select a subset of items where each item can be taken any number of times, such that their total weight is at most capital W, while their total value is as large as possible. To come up with a dynamic programming algorithm, let's analyze the structure of an optimal solution. For this, consider some subset of items of total weight at most capital W, whose total value is maximal. And let's consider some element I in it. Let's see what happens if we take this element out of this solution. So what remains is some subset of items whose total weight is at most capital W minus Wi, right? So this is easy. What is crucial for us is that the total value of this remaining subset of items must be optimal. I mean, it must be maximal among all subset of items whose total weight is at most capital W minus Wi. Why is that? Well, assume that there is some other subset of items whose total weight is at most capital W minus Wi, but whose total value is higher. Let's then take the ith item and put it back to this subset of items. What we get actually is the solution to our initial problem of higher value. I mean, its total weight is at most capital W and its value is higher than the value of our initial solution. But this contradicts to the fact that we started with an optimal solution, right? So such trick is known as cut and paste trick, and it is frequently used in designing dynamic programming algorithms. So let me repeat what we've just proved. If we take an optimal solution for a knapsack of total weight capital W and take some item I out of it, then what remains must be an optimal solution for a knapsack of smaller weight. So this suggests that we have a separate subproblem for each possible total weight from 0 to capital W. Namely, let's define value of W as the optimal total value of items whose total weight is at most W. This allows us to express value of W using the values for smaller weight knapsack. Namely, to get a solution, to an optimal solution for a knapsack of size of total weight W, we first take some smaller knapsack and an optimal solution for it and add an item I to it. So first of all, to be able to add an item I to it and get a knapsack of total weight W, we need this smaller knapsack to be of total weight at most W minus Wi. Also, when adding ith item to it, we increase its value by Vi. And the final thing is that we do not know which element to add exactly. For this reason, we just go through all possible n elements and items and select the maximal value. The maximal value of the following thing: value of W minus Wi plus Vi. Having a recurrent formula for value of W that we've just discussed, it is not so difficult to implement an algorithm solving the knapsack problem with repetitions. Recall that we expressed the solution for a knapsack through solutions for knapsacks of smaller weight. This means that it makes sense to solve our subproblems in the order of increasing weight. So we do this in the pseudocode. Initially, we set value of 0 to 0 just to reflect the fact that the maximal possible total weight of a knapsack, the maximal possible total value of a knapsack of weight 0 clearly equals 0. Then we go in a loop from W equal to 1 to capital W. And for each such W, we just compute the corresponding maximum as follows. We go through all items I such that Wi is at most W. And for each such item I, we see what happens if we take an optimal solution of for a knapsack of size w minus wi and add an item I into it. Clearly, in this case, the total value is value of w minus wi plus vi, and the total weight is at most w. So this is a feasible solution for a knapsack of size of total weight w. So we check whether the resulting value is larger than what we currently have. And if it is, we update value of w. In the end, we just return value of capital W. So this algorithm is clearly correct because it just implements our recurrent formula, right? So in particular, this loop just computes the maximum from the previous slide. Now let's estimate the running time of this algorithm. It is not difficult to see that the running time is big O of n multiplied by capital W. Why is that? Well, just because we have two nested loops here. So this is the first loop and this is the second loop, right? The first one has capital W iterations, and the second one has n iterations. What happens inside the inner loop clearly takes just constant time. We conclude this video by applying our algorithm to the example considered a few minutes before. So in this case, we are given 4 items and a knapsack of total capacity 10. We are going to compute the optimal value for all knapsacks of size of total weight from 0 to 10. So which means that it makes sense to store all these values just in an array. So shown here on the slide. Initially, this array is filled by zeros, and we are going to fill it in with values from left to right. So the first non-obvious cell is 2. So this is the first weight for which we can add any item. So in this case, we can actually say that to get a solution for a knapsack of total weight 2, we can get a solution for a knapsack of total weight 0 and add the last element to it. This will also give us plus 9 to the value. So this is the only possible solution for this cell, so we do not even need to compute the maximum. So in this case, the value is equal to 9. So what about value of 3? So in this case, we already have a choice. We can either get an optimal solution for total weight 1 and add the 4th element to it, or we can get an optimal solution for a knapsack of size of total weight 0 and add the second element to it, whose value is 14. So among these two values, the second choice is better. It gives us a solution of value of 14, so we write it in this cell. Now, for value of 4, there are already 3 choices. Let's consider them. So either we can take an optimal solution for a knapsack of total weight 2 and add the last element to it. So this is plus 9. Or we can take an optimal solution for a knapsack of total weight 1 and add the second item to it, so plus 14. Or we can take an optimal solution for a knapsack of total weight 0 and add the third item. So this is plus 16. Right? So in this case, we need to select a maximum among 16, 14, and 9 plus 9, which is 18. In this case, 18 is the maximal value, so we write it in this cell. So by continuing in the same manner, we can fill in the whole array and see that the last element is equal to 48, which justifies that the optimal value for this knapsack with repetitions problem is equal to 48. And also let me remind you that this optimal value can be obtained by taking one copy of this item and 2 copies of the last item. In the next lecture, in the next video, we will learn how to solve this problem when repetitions are not allowed.